Hello and welcome to the first video of the M3 chapter, Further Centers of Mass. An M2 question on the screen to review a key point that we're going to use in this chapter. Find the center of mass of the following system of particles. The method from M2 that I want to emphasize here is the table that we used. So we've got three different particles, the red, the green and the blue, and then we've got the system as a whole. And in M2 we had here mass, or for a few questions we had relative mass, the x coordinates and the y coordinates. So for the red we've got 2 kilograms, the green 3, the blue 4, total system mass 9 kilograms. The x coordinate of each particle 2, 4, 5, and the x coordinate of the center of mass of the system we called x bar. The y coordinates 1, -1 and 3, and here y bar. And then we applied this formula here, which says the center of mass of the system times the sum of the mass of the system, that's this one here, is equal to the sum of the individual bits, the individual mass times the individual center of mass for each particle, this times this. So this times this, plus this times this, plus this times this, had to equal this times this. We get 4 plus 12 plus 20 must equal 9x bar, which gives us 36. So x bar is equal to 4. And then we can do the same with y bar. So the y coordinate gives us 2 times 1 plus 3 times -1 plus 4 times 3 is equal to 9 times y bar, 11, 9y bar. Y bar is equal to 11 over 9. And if you remember, this was not just for particles on a plane, but also for non-uniform laminas, where we split a lamina into separate pieces, found the center of mass of each piece, and then applied this process to each of the pieces of the lamina as if they were particles on a plane, just like this. And that's why we're reviewing this, because we're going to do that in this chapter. An overview of the chapter: we're going to use calculus to find the center of mass of a uniform lamina in this video. Then we're going to find the center of mass of a uniform body, which is a 3D shape, and then find the center of mass of a non-uniform composite body. In M2 we used symmetry and standard results for uniform laminas. In M3 we're still going to look at uniform laminas, but you need to be able to use calculus to find the center of mass. This is important because it allows us to derive the standard results used in M2, specifically those we didn't actually talk about where they came from, and find the center of mass of non-standard shapes, and even 3D uniform bodies. It's also important because some of your exam questions might specify to use calculus. So if we have a uniform lamina on an xy coordinate grid, so something like this, where this curve here is f of x, or y, and the uniform lamina is the area underneath the curve, we can split this into thin strips of width delta x. So if I use a single line to represent a very thin strip, this has height y, or f of x, and it has width delta x. And this is probably something you recognize from your original work on integrating to find the area under a curve, but we're not just interested in the area here, we're interested in the center of mass of each strip. So the strip we've got here is a very thin, very tall rectangle, and we know the center of mass in a rectangle lies at its geometric center. So here it'll be about here, half of the width and half of the height. But as delta x gets smaller and smaller and tends towards 0, this strip becomes thinner and thinner, and the x-coordinate of the center of mass just becomes whatever the x-coordinate of the strip is. The y-coordinate stays as y over 2. So as delta x tends to 0, the rectangular strips have height y and center of mass at their midpoint x, y over 2. So I've just put 1 on there, but obviously we split this area into lots and lots of different strips, and each strip has its midpoint here as the center of mass. And then we just treat the full lamina shape as a summation of lots and lots of these little strips in here, all the way along. We can sum these together, like we did in the starter question, using the formula that we had from M2. Here I've used a non-vector form of r because we're not going to use vectors, but I also don't want to write the x formula and the y formula each time. So the r here represents x and y both. But before we go ahead and apply this in this situation, we're going to have a quick note on something called rho. Now rho is the Greek letter you can see here. Kind of looks a bit like a P, but it's not. And usually this represents density. So it would be mass per unit volume, which we call density. But we shouldn't really use the word density in what we're doing at the moment, because we're not talking about three-dimensional shapes. This is not mass per unit volume, but mass per unit area. And it's the same idea, but we don't have a specific word for this. We just have to call it mass per unit area. And if you think back to what we did in M2, for frameworks, we would also have mass per unit length. And rho represents all three of these in different contexts. So whichever one you need is the one it represents. Here we're talking about laminas, so it's mass per unit area. So we've still got our shape, and using rho allows us to be a little bit more detailed than what we had in M2, where in M2 we were just talking about relative mass, and I said area is effectively relative mass. What we have here is actual mass by taking the mass per unit area rho and multiplying it by the area. So this gives us mass. And this is very similar to what we did in M2, but just a little bit more detailed. And of course what we want, and what we're talking about here, is the little strip y delta x. And the mass of that little strip then is equal to the mass per unit area times the area of this strip, which is y times delta x, if again we're thinking of it as a very, very thin rectangle. So the area of that is y delta x, and the mass is rho times y delta x. So for a plain lamina, in the formula that we had, we can replace mass with mass per unit area times the area, because in these questions area tends to be the thing that we actually know, and mass is always the thing that we want. So in terms of the formula, we can change the mass here of the individual strip and the mass here of the individual strip into rho y delta x, which is still the mass of the individual strip, just written in terms of mass per unit area and area. So although it looks a little bit different, we are still applying this same idea. So as delta x tends to 0, we said that the rectangular strips have height y and center of mass at their respective midpoints. So again, there's our strip. Center of mass here, and that's at x, where x is just the coordinate of the strip, and y by 2, the midpoint of the line. Then we're applying this formula here, so that we can sum together all of the different strips using their respective centers of mass. So for the x coordinate, this is going to become x bar. This will stay the same. Most of this will stay the same, and we know the x coordinate of the center of mass is just x for each strip in turn. So that gives us this for the center of mass of the x-coordinate of the entire uniform lamina, where I've just divided through by this sum to get x bar by itself, and this has become x. For the y-coordinate, I'm going to do the same, change the r's into y's here, and then divide through by this, and the y-coordinate of the center of mass of each strip we know is y over 2. So that gives us this formula. Finally, then we can integrate as we take this to its limit, delta x tends to 0, the summations become integrals. We get this for the x-coordinate, and this for the y-coordinate. A quick recap then, we started off with our uniform lamina, we split it into strips. Each strip had a center of mass at its geometric center, and as the width tended to 0, the center became effectively a midpoint of a line, with coordinates x, y over 2. Then we applied what we did in the starter question, the formula this slightly altered so that the mass was written in terms of area and mass per unit area, substituted these two in for the x and the y respectively, then integrated. So if we have a uniform lamina on an xy coordinate grid, the coordinates of the center of mass are given by these two formulas here. In the textbook they continue this and they say if you're going to use it like that, then you could just cancel rho and end up with this. Or if you know what the mass of the full lamina is, then this thing on the bottom here, this is just the mass of the lamina. Rho, mass per unit area, and then the integral of y dx you should recognize as the integral of this, which is just the area under the curve. So this thing on the bottom is still just the total mass of the lamina, and if you take that back up on the other side and just call it capital M, as we used to have in M2, then you get this. And of course you have to keep rho in here this time, you can't cancel it because rho has been used to form capital M over here. And of course you can do the same thing with the y coordinate, and have m y bar is equal to the integral of a half rho y squared dx, or y bar the integral of a half y squared dx over the integral of y dx. If you find it very easy to memorize things, it might be worth remembering one of these pairs of formulas. However, what's much more useful, as you'll see as we go through the examples, is to understand where they've come from, to be able to go through this process for a few slightly different situations. There are 6 examples in the textbook. I'm going to go through each one of them to try and emphasize that point. First example here. Use calculus to find the position of the center of mass of a right-angled triangular lamina OPQ with base D and height H. First of all, let me put that on a grid. The base is D and the height is H. And it's coming out from the origin, O. So this is point P and this is point Q. Hopefully you remember where the center of mass is for a triangle from M2, but here we're being told use calculus. So we have to go through this process. First thing I notice about this question is that we don't have a function. We're going to need to work out the function here in order to get the area underneath it. It's quite straightforward though, because it's a straight line. We have y is equal to some multiple of x, the multiple being the gradient. If we know that this is h and this is d, then the gradient is h over d, and the function is h over dx. Now we can just put this into our formulas. For the x coordinate of the center of mass, we've got the integral from 0 to d of rho times x times y, which is h over dx, dx, all divided by, from 0 to d, rho h over d x dx. The two rows cancel out, as do the h over d fractions. So in the numerator we're integrating x squared, which gives us 1/3 x cubed from 0 to d. In the denominator we're integrating x, which gives us a half x squared from 0 to d. Because of the 0 there, that makes it quite easy. We've got d cubed over 3 over d squared over 2, which gives us 2d over 3, which agrees with what we know about triangles. The center of mass of the lamina should be 2/3 along this line here, because it should be 2/3 along this median. For the y coordinate, different formula, same idea. Integrating 1/2 rho y squared, h over d x squared, divided by the integral rho h over d x dx from 0 to d, 0 to d. Again, the rows cancel out. H over d on the bottom cancels out with one of the h over d's on the top. That gives us half h over d x squared over x. So the denominator is the same, that's going to give us d squared over 2. The numerator is different. So that will give us hx cubed over 6d, 0 to d, over x squared over 2, 0 to d. And again, the zeros make this quite easy. hd cubed over 6d over d squared over 2. And if we cancel all of those d's, we end up with h over 3 Again, exactly as we expect, 1/3 of the way up from the base to this point because it's 1/3 of the way up from this median going this direction. Second example. Find the coordinates of the center of mass of the uniform lamina bounded by the curve with the equation y equals 4 minus x squared, the x-axis, and the y-axis as shown in the diagram. So we have the function given to us. This part here, we can see in the diagram the lamina is the area underneath that curve, bounded by the axes. Nothing funny going on here. We can apply these formulas. For the x-coordinate, we have the integral of rho x 4 minus x squared, all divided by the integral of rho 4 minus x squared dx. And this is going from 0 to 2 in both cases. The rows will cancel out, so I'll expand the brackets and integrate. On the top we get 2x squared minus x to the 4 over 4. From 0 to 2, in the denominator, 4x minus x cubed over 3. 0 to 2. Putting in the limits gives us 4 minus 0 on the top and 16 over 3 minus 0 on the bottom for a final answer of 3/4. The y-coordinate, half rho 4 minus x squared squared, 0 to rho 4 minus x squared dx. Again, the rows cancel out. We're just repeating ourselves in the denominator, but for the numerator, if I quickly expand this on the side, we've got 16 minus 8x squared plus x to the 4, and all of that is times by half. So we end up with 8x minus 4x cubed over 3 plus x to the 5 over 10. Just copying this from the one above, and again 16 over 3 minus 0 from the one above, putting the limits into this one on the top, gives me 128 over 15 minus 0 for a final answer of 8 over 5. On the diagram then, that puts the centre of mass approximately here. Example number 3. A uniform semicircular lamina has radius r centimeters. Find the position of its center of mass. This is the first example where applying these two formulas blindly will not give us the correct answer. We need to just be a little bit more careful. So if we've got a semicircular lamina, like this, radius r, then here we've actually got two options. We can work with these formulas here and manipulate them to fit this situation, or we could talk about r and theta, but because r and theta come up in a later example, I'm going to stick with x and y here to show you that we can use these ideas even though the formulas won't always be exactly the same. We can see that very quickly if we take a strip here of the lamina. Straight away you can see that the length of this strip is not y but 2y. It also means that the centre of mass is x, that's fine, as it was before, but not y over 2, but 0. So although in some ways this is a bit more complicated example because of what we're going to do for the x-coordinate, for the y-coordinate it's a much easier example because I can see it's just 0 by the symmetry of the shape. What we need to really be careful of though is the fact that this is 2y and not y, because in our formula here, this little bit here, y dx and y dx down here, this was the area of each strip times by the mass per unit area. The area of each strip in this case is not y times delta x though, it's 2y times delta x. So this y should be a 2y in this formula for this shape, and so it should be on the top as well. Another reason this example is a little awkward is because of the function we have to use. We know that for a circle, x squared plus y squared equals r squared, so to get y in terms of x, we've got r squared minus x squared square rooted, which is not the nicest thing in the world to integrate. We'll come back to that in a second. So for the x-coordinate, the adjusted formula is the integral from 0 to r of rho times x times 2 lots of y, which is the square root of r squared minus x squared, dx. In the denominator, the integral from 0 to r rho 2 times r squared minus x squared to the half dx. Stopping to take a quick look at this, in the numerator we're going to be okay, because the 2 and the x here is a derivative of this bracket in here, more or less. So we can integrate this using the pattern a function multiplied by its own derivative. In the denominator though, it's a little bit more awkward. A much easier way to do this would be to realize that we know the area of a semicircle, unlike the previous example where we didn't know the exact area of that shape. Here we do. This is just pi r squared over 2. So instead of doing this, remembering where that comes from, we can change this back into just the mass of the total shape. And I'll put that over here as a capital M for now, so I can do all my integrating on the right, keeping in mind that M is equal to rho pi r squared over 2. So now we can focus on the integration, and this gives us rho as a constant, integral 0 to r 2x r squared minus x squared to the half dx, which I said by inspection we can see that this is the derivative of this except for a minus, so we're going to have minus rho r squared minus x squared to the 3 over 2 times by 2 over 3. The limit's there from 0 to r. In this case, putting in 0 doesn't give us a 0 overall, but putting in r does give us a 0. R squared minus r squared is 0, so all of this is 0. So this gives us 0 minus rho r squared to the 3 over 2 is r cubed times 2 over 3. Tidying all of that up, we get 2/3 rho r cubed. And on the left, if I put m in now, we get rho pi r squared over 2 times x bar. The rho's then eventually do cancel out still. R squared cancels with that, and we get 4r over 3 pi for the x-coordinate of the centre of mass of the semicircular lamina. And you probably recognise this as a standard result. This you can get directly from a formula in the formula booklet, and if you have to use it in an exam you can just quote it, but if you are asked to prove it in an exam then you'll have to go through this process. So it's good to be aware of how to do this. Next example. The diagram shows a uniform lamina occupying the shaded region bounded by the curve with the equation y equals square root of x on top here, and the straight line with the equation y equals a half x here. Find the coordinates of the centre of mass of the lamina. Okay, again we've got to be really careful here. First of all, I'm going to call this y1 and y2, so I can refer to them in my equations. But we can't just apply this blindly, because it's not going to be correct. First of all, we need to consider the strips that we're using. So if I put on a strip here, then the strip was important for the two reasons of the area and the coordinates of the centre of mass. So the area here is not just y times delta x, this is going to be y1 minus y2 times delta x. So we've got y1 minus y2 times delta x times rho integral, and that will be the denominator. So instead of the y here, here, and here, we're going to have y1 minus y2. But the y squared here is made up of two y's. One y has come from the same as here, that's going to be y1 minus y2, and the other one with the divided by 2, y over 2, came from the centre of mass, the y-coordinate of the centre of mass. So we need to consider that, because that's not going to be y1 minus y2. The centre of mass here, for the x-coordinate is fine, it's just going to be x, so that's okay. Once we change these two y's into y1 minus y2, this one's finished. But the other y in here, that was y over 2, the centre of mass here for the y-coordinate is going to be y1 plus y2 divided by 2. So the divided by 2 is still there, but the other y in here, one of them's y1 minus y2, the other one is going to be y1 plus y2. So you've really got to know what's going on with these strips in order to manipulate the formulas to suit various questions. So here our x-coordinate is going to be the integral rho x y1 minus y2 dx over the integral rho y1 minus y2 dx, and the y-coordinate is going to be the integral rho over 2 y1 minus y2 times y1 plus y2 dx divided by rho y1 minus y2 dx. So a quick recap, this, and this have all come from considering the area of this strip. This one with the divide by 2 here is the y-coordinate of the centre of mass here. I haven't put divided by 2. And the x is still just the x-coordinate as it was before. Now we've got our formulas suitably adjusted for this situation, we can go ahead and do the integrating. Cancelling the rho, that will give us the integral, and we're going from 0 to 4 on all of these. So 0 to 4 of x times the square root of x minus a half x. And the integral from 0 to 4 of the square root of x minus a half x. I don't have a whole lot of room left, so I'm going to expand the brackets x 3 over 2 and integrate in one go. X 5 over 2, 2 over 5, minus a half x squared gives me x cubed over 6. It's going to go from 0, which is a nice number, to 4. Here we're going to have x to the half, so that's x 3 over 2, 2/3, minus x squared over 4. That gives me 32 over 15 minus 0 in the numerator, and in the denominator 4 over 3 minus 0, giving a final answer of 8 over 5. For the y-coordinate, going through all of that, the rows cancel. Integral 0 to 4 square root of x minus a half x times the square root of x plus a half x, not forgetting the half in the front. And in the denominator, I'm just going to skip all the way across to 4 over 3 because that's the same as it was here. I shouldn't jump this step, but I am running out of room, so I'm going to squeeze it up here. Half integral 0 to 4 x minus x squared over 4 dx. Zero to 4. And that also gives 4 over 3. Which gives us a final y-coordinate of 1. So on our diagram, the centre of mass is about here. Next example. Use calculus to find the centre of mass of a uniform lamina in the form of a sector of a circle, radius r, centre O, which subtends an angle 2 alpha at O. This is a proof of the standard result in the formula booklet. This is one of the two examples where we're going to use theta. So we have the sector of a circle coming out like this. At O, the angle subtended is 2 alpha, and I've positioned it such that alpha is on this side and alpha is on this side, so the line of symmetry is along the x-axis, which immediately tells us the y-coordinate of the centre of mass is 0. But to find the x-coordinate of the centre of mass, we need to be very careful here. I'm not going to apply this. What we're going to do is apply a very similar process to the process by which we found this. We're going to get a small section, in this case a sector, like so, where this angle of the sector is going to be d theta, and we'll decrease theta so that these two parts come together, closer and closer, and this angle here will tend towards 0. So while on previous examples we've had a small strip of the lamina be a rectangle, in this case our tiny strip is going to approximate a triangle. As this angle gets smaller and smaller, the curve on the end here gets less and less important, and we get something very close to a triangle. And we know the centre of mass of a triangle is 2/3 of the way down from the vertex. We're not going to worry about the distance this way of the centre of mass. It's going to go through the middle of it, and as d theta gets closer and closer to 0, that's going to effectively be one small strip. If I draw it again, we're going to get something so close together that you can't even see the difference between the two sides. Even though it's slightly triangular, we're going to have the centre of mass 2/3 of the way down there, but the difference in this direction is negligible. So the shape is going to be split into many strips like this, and we're going to apply the same basic principle from M2 that we had before. X bar times the total mass is equal to the sum of the individual strips, mass times their centre of mass. We know where the centre of mass is. It's 2/3 of the way down this strip, and obviously the length of the strip is equal to the radius of the full circle. So that's 2/3 r, and the x-coordinate of that, if I bring the little foot of the perpendicular down here, is going to be 2/3 r cosine theta. So that gives us the centre of mass x-coordinate for all of the individual strips. It's going to depend on theta and r, but r won't change, theta will change. That's this angle here from the x-axis. But we also need the mass here and here of the individual strips. On the left hand side, I don't need to worry too much about getting the individual strip mass, because we could just calculate the area of this and times it by rho. The area of the sector, the full sector that is equal to half r squared theta, and for the full sector we know that theta is equal to 2 alpha, so that becomes r squared alpha. But the very small area of the very small sector we've got as the strip, call that area of the small sector, that also is equal to a half r squared theta, but in this case theta is not this theta round from the x-axis, it's the theta inside the tiny sector here, which is d theta. So that's a half r squared delta theta. So a quick recap there. We've got the x-coordinate of the full sector that we're trying to find, the sum of all of the masses of the individual small sectors, which we're not going to actually sum together because we know the mass of the full sector is this. Missed out a row there, that should be a row times this. The area of the individual sectors is this, again times by a row. But now I've multiplied those two areas by rho, I've realised in the editing process that they should both now be the mass of the sectors respectively. And the x-coordinate of each individual sector is 2/3 r cosine theta. So putting these three things into here, we get x bar times r squared alpha rho is equal to the sum of 2/3 r cos theta, that's the x-coordinate of the centre of mass, times a half r squared rho delta theta, that's the mass of the small sectors, and then we're going to integrate that, so I'll change that to a d theta, and we're going to integrate from minus alpha to alpha around the sector this way. I can immediately tidy this up a little bit because the two rows are just constants, they will cancel. R is also a constant, so the r squared can cancel there. I can pull out the numbers, the 2's cancel. So we get r over 3 integral minus alpha to alpha cosine theta d theta. And on the left we've still got x bar alpha. The integral of cos theta is sine theta. And that goes from minus alpha to alpha, which gives us r over 3 sine alpha minus sine of minus alpha. But remembering a bit of trigonometry, if we want to change this sine of minus alpha into a sine of plus alpha, then we put a minus in front, which makes this a plus as well. So that becomes r times 2 sine alpha divided by 3, and we've got the alpha on the left that I'll divide through by now, to give x bar is equal to 2r sine alpha over 3 alpha. And this is the formula that you get for the centre of mass for a sector of a circle, given in the formula booklet. As with the semicircle earlier, if you have to use this in an exam, you can just use the result given in the formula booklet, but you should understand how to prove it because it might be asked as a proof in the exam. And obviously if you have to prove it, you can't just jump to the formula booklet and say, hey, there it is. You've got to go through this process. Our final example is very similar to this. We're going to prove the result for the arc of a circle. Use calculus to find the centre of mass of a uniform wire in the form of an arc of a circle radius r, centre O, which subtends an angle 2 alpha at O. So we've got a very similar setup, with y here, a shaky x here, arc of a circle here, such that our 2 alpha is split across the x-axis with alpha here and alpha here, so that we can have y bar is equal to 0. And again, we're not really going to use this formula, but we are going to use that same formula from M2, x bar times the sum of the individual masses, i.e. the total mass, is equal to the sum of the individual masses times the individual x-coordinate of the centre of mass of each piece. But the piece we're going to take in this case is not an area, it's going to be a tiny little part of the circumference. Before we do that, let's look at the total mass, because that's going to be a bit easier. We know the length of this arc here is equal to r theta. So the arc is equal to r theta, which means the mass of that arc is equal to rho times r theta, where rho is not the mass per unit area in this example, it's the mass per unit length, because we're looking at a framework. But it does the same job and we can still call it rho. If I call this the total mass of the arc, we get rho r theta, where theta for the total mass is 2 alpha, so we get 2 alpha rho r. And that's this bit here, so I don't need to worry about doing a summation, which will turn into an integration in a moment. It's just going to be this. On the other side, as with the previous examples, it's not quite that simple. I need the individual mass of each section times by its individual centre of mass coordinate, and then sum them together. The individual piece we're going to take here is a little part of the circumference, subtended at an angle delta theta again. But no doubt you can see that as this gets smaller and smaller, we're just going to collapse it down to a single point. And the centre of mass obviously is going to be at that point. So that's still going to be r there. The x-coordinate of that centre of mass then will be r cosine theta. And the r won't change, but the theta will as we go along the arc. So the mass for this little section here is going to be rho r times delta theta. Now we've got the three things that we need. We've got the total mass for this section here, we've got the individual mass here of each little section we're going to take, and the x-coordinate of the centre of mass of each of those sections. So we put these three things into the formula. We get x bar times 2 alpha rho r on the left is equal to the centre of mass, r cosine theta, times the mass of each one, rho r delta theta, and we're going to sum them as delta theta tends to 0, so that's going to become an integration with a d theta, integrating from minus alpha to alpha. As with the previous example, we can cancel a few things here. Rho is just a constant, r is just a constant, so that gives us 2 alpha x bar on the left, and r integral cos theta on the right, minus alpha to alpha, which again is going to give us r sine theta as in the previous example. That's going to give us 2 sine alpha. Now the 2's cancel out, divide through by alpha, and we get x bar is equal to r sine alpha over alpha, which is given in the formula booklet. And again, if you need to use this as part of one of your questions, you can just quote it out of the formula booklet without a problem. But if you need to prove it, obviously you need to go through this process. That's the final example, and I hope these have really emphasized that it's not really so useful to memorize these, although if you find it easy to do that, it might be worth doing. But what's more useful is to understand how this applies in this process, so that for any given shape, you can find the total mass, the mass of an individual section, and the centre of mass of the individual section, put it into this formula here, take it to the limit, and turn it into an integral. So I hope that's enough now for you to have a go at the questions from exercise 5a, and maybe I'll see you in the next video for solid bodies.